Scalar multiplication. The most important operation. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring scalar multiplication on elliptic curves, the single most important operation in elliptic curve cryptography. When you generate a Bitcoin private key, create a TLS certificate, or sign a digital document, you're performing scalar multiplication. This operation is what makes public key cryptography work. It's easy to compute in one direction but nearly impossible to reverse. Scalar multiplication means adding a point to itself multiple times. If p is a point on an elliptic curve and k is an integer, the scalar, then kp means p plus p plus p, k times. For example, 5p equals p plus p plus p plus p plus p, simple concept, but the naive approach of repeatedly adding p would be impossibly slow for the huge numbers used in cryptography. Imagine adding a point to itself a billion times. The breakthrough that makes elliptic curve cryptography practical is an algorithm called double and add, based on binary representation. Instead of k additions, we only need about log base 2 of k operations. For a 256-bit number, that's just 256 operations instead of 10 to the power of 77. We'll derive this algorithm, understand why it works, and compute complete examples showing every algebraic step. The naive approach and why it fails. Let's start by understanding why the obvious approach doesn't work. If we want to compute 5p, we could just add p to itself 5 times. Start with p, add p to get 2p, add p again to get 3p, add p again to get 4p, add p one more time to get 5p. That's 4 addition operations. For small numbers like 5, this is totally fine. But in cryptography, we do not use small numbers. A typical private key in Bitcoin is a 256-bit number. That is roughly 10 to the power of 77, a number with 77 digits. If we tried to compute kp by adding p to itself k times, we would need 10 to the power of 77 additions. Even if each addition took 1 nanosecond, which is unrealistically fast, the total time would be longer than the age of the universe. Clearly, we need a better approach. The insight is to use the binary representation of k. Any integer can be written as a sum of powers of 2. For example, 13 equals 8 plus 4 plus 1, or in binary, 1101. So 13p equals 8p plus 4p plus p if we can compute powers of 2 times p efficiently, meaning 2p, 4p, 8p, etc. Then we can compute any multiple of p by adding the appropriate powers together. How do we compute powers of 2 efficiently? Through repeated doubling. 2p is just p plus p, then 4p equals 2p plus 2p, which we can compute by doubling 2p. Then 8p equals 4p plus 4p, computed by doubling 4p. Each doubling gives us the next power of 2. For a k-bit number, we need only about k doublings plus a few additions, a logarithmic algorithm instead of a linear one. This is the double and add method. Point doubling. The foundation. Before we can implement double and add, we need to understand point doubling algebraically. Point doubling is computing 2p equals p plus p, adding a point to itself. You might think we can just use the regular point addition formulas, but there is a problem. When we add p to itself, both points have the same coordinates. So x2 equals x1 and y2 equals y1. The slope formula lambda equals y2 minus y1 divided by x2 minus x1 becomes 0 divided by 0, which is undefined. The solution involves using calculus. Instead of calculating the slope of the line passing through points p and q, we use the slope of the tangent line to the curve at point p. This tangent line represents the limiting case. As point q approaches point p to determine this slope, we implicitly differentiate the curve's equation. The curve is defined as y squared equals x cubed plus ax plus b. Differentiating both sides with respect to x, we get 2y times dy dx equals 3x squared plus a. Solving for dy dx, we find that dy dx equals the quantity 3x squared plus a, divided by 2y. At point P equals x1, y1, the slope is lambda equals 3x1 squared plus a, divided by 2y1. This is our doubling slope. Once we have lambda, we use the same formulas as regular addition. x3 equals lambda squared minus 2x1. We subtract 2x1 instead of x1 plus x2 because both points are the same, and y3 equals lambda times x1 minus x3, minus y1. These are the point doubling formulas. Point doubling is slightly faster than general point addition because we don't need to compute x sub 2 minus x sub 1 or y sub 2 minus y sub 1, as we know both differences are zero. In optimized implementations, doubling can be about 20% faster than addition. Since the double and add algorithm uses many doublings, this performance difference adds up and makes elliptic curve cryptography practical for real-world use. Binary representation. The key insight. The double and add algorithm is based on representing the scalar k in binary. Binary is base 2. Every digit is either 0 or 1, and each position represents a power of 2. For example, the binary number 101 means 1 times 4 plus 0 times 2 plus 1 times 1, which equals 5 in decimal. The binary number 1101 means 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, which equals 13. Here's the key insight. If k equals the sum of powers of 2, then kp equals the sum of those powers of 2 times p. For example, since 13 equals 8 plus 4 plus 1, we have 13p equals 8p plus 4p plus p. So if we can compute 8p, 4p, and p, we can add them together to get 13p. We already know p, it is given, and we can get 8p and 4p through repeated doubling. The algorithm processes the binary digits from left to right. We start with the leftmost 1 bit, which always exists for positive integers, and initialize our result to p. Then, for each remaining bit, we double the current result. This shifts us to the next power of 2, and if the current bit is 1, we add p. This way, we build up the result incrementally, doubling to move between powers of 2 and adding p when needed. Let's trace through 13p equals binary 1101. Start with the leftmost one. The result equals p. The next bit is 1. Double to get 2p, then add p to get 3p. The next bit is 0. Double to get 6p, but do not add. The next bit is 1. Double to get 12p, then add p to get 13p. That's 4 doublings and 2 additions, for a total of just 6 operations, instead of 12 additions with the naive approach. And the savings become exponentially better as k increases. The double and add algorithm. Let's formalize the double and add algorithm as a step-by-step procedure. The input is a scalar k, a positive integer, and a point p on an elliptic curve. The output is the point kp. Here is the algorithm. First, convert k to binary representation. Write k as a sequence of bits. b sub n minus 1, all the way down to b sub 1, b sub 0, where b sub n is the most significant bit, which is always 1 for positive k, and b sub 0 is the least significant bit. Second, initialize the result. Set result equal to p. This handles the most significant bit, which is always 1. Third, process each remaining bit from left to right, for I from n-1 down to 0. Double the current result. Result equals 2 times result. And if bit b sub I equals 1, add p to the result. Result equals result plus p. Fourth, return the final result, which equals kp. Why does this work? Think about what happens at each step. When we double, we're multiplying the current result by 2. When we add p, we're adding 1 times pages as we process the bits from left to right. We're essentially computing p times 2 to the power n, then optionally adding p, then multiplying by 2, then optionally adding p, and so on. This builds up k digit by digit in binary. The algorithm requires at most n doublings, 1 per bit, and at most n additions, 1 for each 1 bit. Since n equals log base 2 of k, that's at most 2 log base 2 of k operations total. For a 256-bit number, that's at most 512 operations, astronomically fewer than 10 to the power of 77. This logarithmic complexity is what makes elliptic curve cryptography feasible. Without double and add, public key cryptography as we know it wouldn't exist. Example setup. Computing 5p. Let's work through a complete example. Computing 5p on the curve y squared equals x cubed minus 2x, starting with point p equals 2, 2. First, let's verify that p is actually on the curve. On the left side, y squared equals 2 squared, which equals 4. On the right side, x cubed minus 2x equals 8 minus 4, which equals 4. Yes, 4 equals 4, so p is on the curve. Next, convert 5 to binary. 5 in binary is 1, 0, 1. This means 5 equals 4 plus 1, or 5 equals 1 times 4 plus 0 times 2 plus 1 times 1. So, we will need to compute 4p and 1p, then add them. The binary representation tells us exactly what operations to perform. Start with p, the leftmost one. Double to get 2p. Process the 0. Double again to get 4p. Process the next power. Then add p, the rightmost one. Let's trace through the algorithm step by step. The binary representation of 5 is 1, 0, 1. To initialize, the result equals p, which equals the coordinates 2, 2. This step handles the first 1 bit. Next, process bit 1, which is 0. We double the current result to obtain 2p, then process bit 0, which is 1. We double the result again to get 4p, and then add p to obtain 5p. Therefore, we will need to compute 2p by doubling 2, 2, then compute 4p by doubling 2p, and finally compute 5p by adding 2, 2 to 4p. For this example, we'll use the curve y squared equals x cubed minus 2x. So a equals negative 2 and b equals 0. We'll show every algebraic calculation explicitly, computing slopes, finding x coordinates and y coordinates, and verifying results. This will demonstrate that scalar multiplication is just repeated application of the point doubling and point addition formulas we've already learned. Computing 2p. Point doubling. Let's compute 2p where p equals 2, 2 on the curve y squared equals x cubed minus 2x. We use the point doubling formulas. The curve has a equals negative 2, so we will need that in our slope calculation. First, compute the slope lambda. For doubling, lambda equals 3x sub 1 squared plus a divided by 2y sub 1. With x sub 1 equals 2, y sub 1 equals 2, and a equals negative 2. Numerator equals 3 times 2 squared plus negative 2 equals 3 times 4 minus 2 equals 12 minus 2 equals 10. Denominator equals 2 times 2 equals 4. So lambda equals 10 divided by 4 equals 5 halves. Second, compute x3. x3 equals lambda squared minus 2x1. We have lambda equals 5 over 2 and x1 equals 2. So, x3 equals 5 over 2 squared minus 2 times 2 equals 25 over 4 minus 4 equals 25 over 4 minus 16 over 4 equals 9 over 4. The x-coordinate of 2p is 9 over 4. Third, compute y3. y3 equals lambda times x1 minus x3 minus y1. We have lambda equals 5/2, x1 equals 2, x3 equals 9/4, and y1 equals 2. So, y3 equals 5/2 times 2 minus 9/4 minus 2. Now 2 equals 8/4. So 2 minus 9/4 equals negative 1/4. Therefore, y3 equals 5/2 times negative 1/4 minus 2 equals negative 5/8 minus 2 equals negative 5/8 minus 16/8 equals negative 21/8. The y-coordinate of 2p is negative 21/8. So, 2p equals the point with coordinates 9/4, negative 21/8. Let's verify that this point is on the curve. For the left side, negative 21/8 squared equals 441/64. For the right side, 9/4 cubed minus 2 times 9/4 equals 729/64 minus 18/4, which then equals 729/64 minus 288/64, finally resulting in 441/64. Perfect. Both sides equal 441/64, confirming that 2p is indeed on the curve. Now, we can proceed to compute 4p. Computing 3p. Adding 2p and p. Now, we will compute 3p by adding 2p plus p. This demonstrates point addition, not doubling, since we are adding two different points. We have 2p equals 9/4, negative 21/8, and p equals 2, 2. Let us use the general point addition formulas, where point 1 is 2p and point 2 is p. First, let's compute the slope lambda. The formula for lambda is y sub 2 minus y sub 1, divided by x sub 2 minus x sub 1. Given our values, x sub 1 is 9/4, y sub 1 is negative 21/8, x sub 2 is 2, and y sub 2 is 2. To find the numerator, we calculate 2 minus negative 21/8. This simplifies to 2 plus 21/8. By converting 2 to an equivalent fraction of 16/8, the numerator becomes 16/8 plus 21/8, which equals 37/8. Next, for the denominator, we have 2 minus 9/4. Converting 2 to an equivalent fraction of 8/4, the denominator becomes 8/4 minus 9/4, resulting in negative 1/4. Therefore, lambda is 37/8 divided by negative 1/4. To perform this division, we multiply 37/8 by the reciprocal of negative 1/4, which is negative 4/1. This multiplication yields negative 148/8. Finally, simplifying this fraction, lambda equals negative 37/2. Second, compute x sub 3. X sub 3 equals lambda squared minus x sub 1 minus x sub 2. Substituting the values, this calculation becomes negative 37/2 squared, minus 9/4, minus 2. We then find that negative 37/2 squared equals 1369/4. Converting 2 to fourths, we get 2 equals 8/4. Therefore, x sub 3 equals 1369/4 minus 9/4 minus 8/4, which simplifies to 1352/4, or 338. The x-coordinate of 3p is 338. Third, compute y3. y3 equals lambda times the quantity x1 minus x3, minus y1. Substituting the values, this equals negative 37/2 times the quantity 9/4 minus 338, minus negative 21/8. Now, 9/4 minus 338 equals 9/4 minus 1352/4, which then equals negative 1343/4. So, negative 37/2 times negative 1343/4 equals positive 49,691/8. Then, 49,691/8 minus negative 21/8 equals 49,691/8 plus 21/8, which totals 49,712/8, finally equaling 6,214. Therefore, 3p equals the coordinates 338, 6,214. Notice how quickly the coordinates grow with real numbers. This is why cryptography uses finite fields to keep numbers bounded. Complexity analysis. Why double and add works. Let's analyze why the double and add algorithm is so much faster than the naive approach. The naive method of adding p to itself k times requires exactly k-1 addition operations. For small k, this is fine, but for cryptographic keys, it becomes completely impractical. The complexity is big O of k, linear in the size of the scalar. The double and add algorithm, on the other hand, has complexity big O log 2k. Here's why. If k is an n-bit number, then n equals log 2k approximately. We process each bit once, performing at most one doubling and possibly one addition per bit. So we need at most n doublings and at most n additions, giving us a total of at most 2n operations. Since n equals log 2k, that's at most 2 log 2k operations. The table on the slide shows concrete comparisons. For k equals 10, the naive method requires 9 additions, while the double and add method needs about 6 operations. This results in a modest 1.5 times speedup. For k equals 100, the naive method requires 99 additions, whereas the double and add method needs only about 13 operations. This makes us 7.6 times faster. For k equals 1000, the speedup reaches 66 times. You can see the pattern. As k grows, the advantage of double and add grows exponentially. Now, here is where it gets truly dramatic. For a 256-bit number like those used in Bitcoin and Ethereum, k is approximately 2 to the power 256, which is roughly 10 to the 77th power. The naive method would need about 10 to the 77th additions. The double and add method needs only about 512 operations. That is around 256 doublings, plus up to 256 additions for the 1 bits. The speedup factor is approximately 10 to the 74th power. Without this exponential improvement from big O of k to big O of log k, elliptic curve cryptography would be completely impractical. A computation that would take longer than the age of the universe becomes something that completes in microseconds on a modern computer. This is why double and add is not just an optimization. It is the fundamental breakthrough that makes ECC possible. Summary and cryptographic applications. We've learned that scalar multiplication, KP, is computed efficiently using the double and add algorithm, which is based on the binary representation of k. Instead of k additions, we need only about log base 2 of k doublings, plus the additions for each 1 bit. For a 256-bit number, that's about 256 to 512 operations. This is practical for computers, yet the inverse operation, given kp, find k, is essentially impossible. This one-way property is the foundation of elliptic curve cryptography. In ECDSA, used in Bitcoin, your private key is a random number k, and your public key is kg, where g is a standard generator point. Anyone can verify signatures using your public key kg, but they can't recover your private key k. In ECDH, used in TLS, two parties exchange public keys kg and lg. Then both compute the shared secret klg using their own private key. An eavesdropper sees kg and lg but can't compute klg. The algebraic formulas we've studied, point addition, point doubling, and double and add, are exactly what's implemented in cryptographic libraries. The only difference is using finite fields instead of real numbers, which keeps the coordinates bounded and makes the arithmetic fast. The same formulas, the same algorithm, just different numbers. That's the power of abstract algebra. Derive it once, use it everywhere. Understanding scalar multiplication algebraically gives you deep insight into why elliptic curve cryptography is secure and efficient. The security stems from the difficulty of the discrete logarithm problem. Specifically, given kp, it is hard to find k. Its efficiency comes from the speed of the double and add operation, as computing kp takes logarithmic time. Together, these properties enable the secure, high-speed cryptography that protects the modern Internet. Thank you for your attendance. Please consider subscribing to the channel.